In this video, we're going to talk about the Arrhenius equation. The Arrhenius equation is an equation that maps the relationship between the temperature of a reaction and the rate constant. Okay, so if you recall from previous videos, the rate constant is a constant at a specific temperature. If the temperature changes, the rate constant changes. And the Arrhenius equation is what maps that change of between temperature and rate constant. So let's take a look at it. So this is the form of the Arrhenius equation. You have rate constant K is equal to A times E raised to the power of negative EA over RT. Maybe we should put this in parentheses out here to make that clear. So E is raised to that entire thing. Now, T out here is the temperature in Kelvin. R is actually the universal gas, the ideal gas constant, which is 8.314 joules per Kelvin per mole. Now, keep one thing in mind. Usually, the ideal gas constant is expressed as 0.0821, but in this case, it's 8.314 because of the activation energy, which is actually given to you in joules. Now, EA is the activation energy out here. And A is something called a frequency factor. So if you recall, when the reactants collide, that's when the reaction takes place. So, but the question is, how fast are they colliding? So the frequency factor gives you an idea, or basically tries to map how fast those collisions take place. Okay, so that's why A is the frequency factor. So there you have it. Okay. Now, usually the Arrhenius equation is not used in this form. Usually what we do is we take a log of both sides and use it in the logarithmic form. So let's go ahead and derive the logarithmic form of this. We'll use the natural logarithm. So I'm going to just take log of both sides. So that's going to give me ln of k is equal to ln of a e minus ea over rt. Okay. Now see, that's the log of two numbers multiplied with each other. So that's going to be ln of A plus ln of E minus EA over RT. Let's put that in parentheses. Okay. Now, because that's an ln with the same base, because that's a natural logarithm, okay, that collapses. Okay. But before that collapse, you can bring that in front. So you get ln of A minus EA over RT times ln of E base E. Now, let me quickly show you on the side how I did that. That's a property of logarithms. My marker is not working, so let me just use a different color. So if I have ln of A raised to B, that is equal to whatever it's raised to, that can be brought forward out here. So that's B times ln of A. That's the relationship I used out here. Now out here, I was talking about collapsing ln of E base E. What that means is if I have ln of, let's say, A base A, that is equal to 1. Okay, anytime you take the log of any number base to the same number, that is equal to 1. So this becomes ln of A minus EA of RT. That's 1, so we just don't worry about it, and there you have it. So that is the form of the Arrhenius equation that we end up using a lot. Now, if you look at this form looks very similar to the equation of a straight line, but we have to do a little bit of rearranging to this. Okay, so we'll keep the ln of K out here. And what we'll do is we switch these two terms around, okay? So that is equal to minus EA over R times 1 over T, okay? So we just separate the T because the T is a variable, it's a temperature. And we're trying to map, remember, the temperature and the rate constant. So that is one variable and K is the other variable, right? So ln of K, okay? So this is actually the X variable, okay? So that's going to be on the horizontal axis, and then we're going to put the ln of A on the right side. So that's my y-intercept. Okay, so now if you plot this, I'm just going to go ahead and erase this side so I can show you the plot. what it'll look like. If you plot this, so we're going to put 1 over t on the horizontal, and we're going to put ln of k on the vertical. Okay, we're going to get a negative slope because of that negative EA over R. So that's the slope. So the slope is equal to negative EA over R. Okay, and there you have it. Okay, so now when you use a straight line, so basically y is equal to mx plus v, when you plot it, so if you have different data points, so you have different values of k, you have different values of t, you can plot them, create a straight line, and from that you can find out the activation energy. So it's a pretty useful form to have available. So if you have two data points, so you have two values of k and two values of t, you can use the 2-point form of the Arrhenius equation. Okay, so the 2-point form becomes ln of k2 over k1 is equal to EA over R times 1 over T1 minus 1 over T2. Okay, so that's the 2-point form. Okay, so let's take a look at a problem where we're using the 2-point form. So let's say you have a certain reaction, okay, and the rate constant doubles when the temperature increases from 15 to 25 degrees Celsius. Okay, so we'll say T1 is equal to 15 degrees Celsius. Remember, we got to change that to Kelvin. Okay, so that's going to be 273 plus 15, which is 288 Kelvin. Okay, and T2 is 25 degrees Celsius. So that's going to be 273 plus 25, that's 298 Kelvin. Okay, and then what they're saying is that the rate constant, it doubles when the temperature increases. Okay, so K1 is simply K1, right? And K2 is equal to 2 times K1. That's how we work it. Now we'll just go ahead and take this information and plug it into this form. Okay, and the question is calculate the activation energy. So if you're trying to calculate the activation energy, so we have ln of K2 over K1. So that's 2K1 over K1 is equal to EA over R is the 8.314 joule per Kelvin mole times 1 over T1 is 288 minus 1 over T2 is 1 over 298, and that's both Kelvin. That cancels out, and then let's go ahead and simplify all of this. All right, so what I did was I worked out this problem, and basically ln of 2 becomes 0.693, and then that's multiplied with 8.314 once you take 8.314 from this side of the equation to this side, and then this entire thing reduces to 0.000113. You take this entire thing divided by that, you get 50987, and when you correct it for significant figures, you get 51000. Actually, it's 510 times 10 to the power 2. Okay,